This is a short video on induction. And what I want to prove for this video, I want to prove this statement, that if I add the numbers 2 plus 6 plus 10 plus 14, this is an arithmetic series now, the general term, the nth term generator, 4n minus 2, these will always total to 2n squared. And I want to prove this is true for all natural numbers. That is, I want to prove that if n is equal to 1, and I just look at the very first term, that will equal 2 times 1 squared. If n is equal to 2, that would be the first two terms added up, 2 plus 6, that will be 2 times 2 squared. And if n is equal to 3, 2 plus 6 plus 10, the first three terms, that will be equal to 2 times 3 squared. And if n is equal to 4, I have the first four terms, that will be equal to 2 times 4 squared. Now, what I can't do is just show that these statements are true. In fact, these statements are true. 2 is the same as 2. This is equal to 8, and that's going to be 2 times 4, which is 8. So that's true. And this is equal to 18, right? And that would be the same as 2 times 9, which is 18. And that's also true. And again, I could go through this whole list. So I have 24, 32, and that's going to be the same as 2 times 16, which is 32. But just because this is true for the first four integers doesn't mean it's going to be true for all natural numbers, and that's what I need to do. Okay, so to do that, I have to use induction. Induction consists of two steps, basically. There's what's called the base case, the bottom step, base case, and that's the simplest case. In other words, I have to show that 2 is equal to 2 times 1 squared, right? And this is take this a sub n, 4 times 1 minus 2, that gave me 2. And I have to show that's equal to putting 1 right there. And that's pretty easy to do. 4 minus 2 is 2, and 2 times 1 is 2. Okay, so it does work in the base case, true. But to get all the natural numbers, I have to do what's called an induction case. And the induction case says, let's suppose this were true for a particular integer. It's typically given the letter k. So we're going to assume that this is true for one integer only, but I'm not going to specify what it is. Assume it's true for k, and we need to show true for the successor. The integer that comes after k would be k plus 1. Okay. So the idea on a series proof like this is you assume this is going to be true for some number k, and that step would look like this: 2 plus 6 plus 10 plus 14 plus all the way out to 4 k minus 2. Notice that's just this nth term generator is equal to k, 2k squared. And again, that's the kth partial sum. So basically, you replace the n in the general statement with the letter k. That's pretty easy to do. We assume this is true. Okay, and then what we need to show is that this necessarily will result in this statement: 2 plus 6 plus 10 plus 14 plus 4k minus 2. Now I'm going to add the next term, the term that comes after this would be 4 times k plus 1 minus 2. And that's supposed to be the thing that would come after this, which would be 2 times k plus 1 squared. So somehow logically we have got to get from this line to this line. And for all series proofs, the method is the same. You basically add to this line right here. you add what comes after 4k minus 2. So this is a sub k. What we're going to add is a sub k plus 1, and that's this. Okay, so this is a sub k plus 1. Okay, and of course, if you add that to the left side of the equal sign, you have to add it to the right side. So this now is s sub k, and we're going to be adding a sub k plus 1. And what we have to do is to show that this is equal to this. Now, it looks like a lot of work, but it really does boil down to two steps. You have to show a sub 1 is equal to s sub 1, and you have to show that a sub k plus 1 plus this kth partial sum will be equal to the k plus first partial sum. Okay, and for our particular series, we already have these facts. We know that a sub n is 4n minus 2, and we know s sub n is equal to 2n squared. So we're going to use those facts, and then we're going to show these two steps. This is the easiest one to show. So a sub 1 is going to be 4 times 1 minus 2, and s sub 1 is 2 times 1 squared. So 4 minus 2 is 2 times 1. 2 is equal to 2. That's true. For this case, things get a little bit more intriguing. So let's see, a sub k plus 1, and we'll do this one first. A sub k plus 1 is 4 times k plus 1 minus 2. Basically, I take my nth term generator, and in place of n, I'm putting k plus 1. Okay, to that, I have to add the kth partial sum. Here's my nth partial sum. So in place of n, I'm going to put k. So 2k squared. And on the right side, I need the k plus first partial sum. So again, go back to your nth partial sum, and in place of n, now you're going to be putting k plus 1 there, and there, k plus 1. So I have 2 times k plus 1 quantity squared. Now, if the statement is true originally, this will be true. I just have to verify that these two sides of the equal sign are the same. 4k plus 4 minus 2 plus 2k squared is supposed to be, I suppose I should have a question mark there, 2 times k squared plus 2k plus 1, expanding the binomial. The right side, 2k squared plus 4k plus 2, right? Just distributing. And the left side, if I just rearrange, I have my 2k squares, there's my 4k's, and 4 minus 2 is 2. And these do match exactly, so I'm done. Okay, let's try another example that will go, let's see how much time we got here, running on 8 minutes. Let me go ahead and stop this one here. You might want to rework this one on your own, take some notes, and then I'll do another quick video, another 8-minute video or so that will give you 2 more examples.